In mathematics, particularly in linear algebra, a flag is an increasing sequence of subspaces of a finite-dimensional vector space V. Here, increasing means each is a proper subspace of the next. See filtration. Opening curly bracket. 0. Closing curly bracket. Equals. V. 0. V. 1. V. 2. V. K. Equals. V. Display style 0 equals V underscore 0 subset V underscore 1 subset V underscore 2 subset CDOTS subset V underscore K equals V. Closing curly bracket. If we write the dim vi equals die, then we have 0 equals D 0 less than D 1 less than D 2 less than D K equals N. Display style 0 equals D underscore 0 less than D underscore 1 less than D underscore 2 less than CDOTS less than D underscore K equals N. Closing curly bracket, where N is the dimension of V, assumed to be finite dimensional. Hence, we must have Kn. A flag is called a complete flag if die equals I. Otherwise it is called a partial flag. A partial flag can be obtained from a complete flag by deleting some of the subspaces. Conversely, any partial flag can be completed in many different ways by inserting suitable subspaces. The signature of the flag is the sequence D1, dk. Under certain conditions, the resulting sequence resembles a flag with a point connected to a line, connected to a surface. Basis. An ordered basis for V is said to be adapted to a flag if the first die basis vectors form a basis for Vi for each 0 ik. Standard arguments from linear algebra can show that any flag has an adapted basis. Any ordered basis gives rise to a complete flag by letting the Vi be the span of the first I basis vectors. For example, the standard flag in Rn is induced from the standard basis E1, n, where A denotes the vector with a 1 in the ith slot and 0 s elsewhere. Concretely, the standard flag is the subspaces 0 less than E1 less than E1, E2, less than E1, En, equals, Kn, display style 0 less than, left langle E underscore 1, right, wrangle less than, left langle E underscore 1. E underscore 2, right, wrangle less than, CDOTS less than, left langle E underscore 1. L dots. E underscore N, right, wrangle equals K caret N. Closing curly bracket. An adapted basis is almost never unique. Trivial counterexamples. See below. A complete flag on an inner product space has an essentially unique orthonormal basis. It is unique up to multiplying each vector by a unit scalar of unit length, like 1, minus 1. I. This is easiest to prove inductively by noting that V I minus 1 less than V I display style V underscore I in V underscore I1 caret perp less than V underscore I, which defines it uniquely up to unit. More abstractly, it is unique up to an action of the maximal torus. The flag corresponds to the Borel group, and the inner product corresponds to the maximal compact subgroup. Stabilizer. The stabilizer subgroup of the standard flag is the group of invertible upper triangular matrices. More generally, the stabilizer of a flag. The linear operators on V such that T, V, I, less than, V, I, display style T, V underscore I, less than V underscore I, for all I, is, in matrix terms, the algebra of block upper triangular matrices, with respect to an adapted basis. where the block size is d I minus d I minus 1. Display style d underscore I1. The stabilizer subgroup of a complete flag is the set of invertible upper triangular matrices with respect to any basis adapted to the flag. The subgroup of lower triangular matrices with respect to such a basis depends on that basis, and can therefore not be characterized in terms of the flag only. The stabilizer subgroup of any complete flag is a Borel subgroup of the general linear group, and the stabilizer of any partial flags is a parabolic subgroup. The stabilizer subgroup of a flag acts simply transitively on adapted bases for the flag, and thus these are not unique unless the stabilizer is trivial. That is a very exceptional circumstance. It happens only for a vector space of dimension 0, or for a vector space over F2. Display style mathbf f_2 of dimension 1. Precisely the cases where only one basis exists, independently of any flag. Subspace nest in an infinite-dimensional space V, as used in functional analysis. The flag idea generalizes to a subspace nest, namely a collection of subspaces of E that is a total order for inclusion and which further is closed under arbitrary intersections and closed linear spans. See nest algebra. Set theoretic analogues. From the point of view of the field with one element, a set can be seen as a vector space over the field with one element. This formalizes various analogies between Coxeter groups and algebraic groups. Under this correspondence, an ordering on a set corresponds to a maximal flag. An ordering is equivalent to a maximal filtration of a set. For instance, the filtration flag, opening curly bracket, 0, closing curly bracket, opening curly bracket, 0, 1, closing curly bracket, opening curly bracket, 0, 1, 2, closing curly bracket, display style 0 subset O1 subset O1 2 corresponds to the ordering 0, 1, 2, display style O1 2, closing curly bracket. See also filtration, mathematics, flag manifold, Grassmannian, Matroid. References: Shafarevich, I. R. A. O. Remizov, 2012. Linear Algebra and Geometry. Springer. ISBN 9783642309939.